Our first speaker is a distinguished speaker, Professor Shavkat Alimov. A while ago we were students. We always admired his mathematics, his leadership skills. He was the rector, minister of education. And I never imagined that there will be a day when I'll be introducing Shavkat Alimov to be our speaker. So without further ado.
Good morning, dear colleagues. It's really a very big pleasure and great opportunity to have the talk here before this distinguished audience. You see, according to the rules, I prepared this PowerPoint presentation, but this morning I understood that there are too many formulas, and if you allow me, I will use this whiteboard to explain some ideas concerned with this phenomenon. I am very proud that Professor Mark Pinsky now is sitting here and is listening to me. Mark. Yeah, okay. And I begin from the beginning, yeah. If you consider Laplace operator, it's a negative operator, but minus delta is a positive operator. We try to study his spectrum eigenvalues, eigenfunctions in some domain omega with some boundary conditions. Or usually we can find the spectrum. It is a sequence of positive numbers, and this is orthonormal system. We suppose that this boundary condition is so that the operator is self-adjoint. In this case, it will be orthonormal system, and each function f may be represented as the sum, scalar product f uk. But it's very difficult to expect that it will be convergent in the sense of L2 if f belongs to L2. But in general case, using computer, we would like to find the uniform convergence. And in this case, we consider usually partial sum. I denote it by E lambda is lambda kt less than lambda. The problem is in case when f is a very smooth function, just in this case too, the behavior of this E lambda f is not good. Let us suppose that E lambda f is very smooth function, but however, it may be that E lambda f in some point x0 is something like, for example, cosine lambda. We suppose that we have some suspicions that f of x0 is 0. But how to prove it? It's oscillating but not converging. Usually we can use the mean value. It means E lambda 1. F 1 over lambda, this E T F. Or it's just this is just sine lambda over lambda. You see, and it tends to 0. It's very good. But sometimes this behavior is something like this. It's worse. But in this case, we can use another mean value, E lambda 2f. Just the same. But here E t1 f, dt, yeah. And this is, again, something like sine lambda or cosine lambda over lambda, it tends to 0. Sometimes we need to consider more general E. If we repeat this procedure s times, it will be E lambda sf. First, this idea was, was developed by Cesaro in case where the spectrum is discrete. It was about 200 years ago. And in this continuous case, it was made by Marcel Ries, who worked in Sweden. And because of that, the name of this mean value is the normal Ries means. And Solomon-Bochner discovered in case when the omega is, how to say, if in periodical case, he discovered that critical value S is n minus 1 over 2. Here n is dimension omega. If S is greater than n minus 1 over 2, in this case, for any continuous function, the convergence is uniform. Convergence of the, it's converging uniformly to f x naught for all x naught for some compact subset. And if S is equal to n minus 1, it's possible to give an example of continuous function. And for this function, this statement is wrong. And because of that, the name of this S is critical index.
For S less than n minus 1.
If, yeah, this is critical index. If S is, I denoted, if F is bigger than S star, in this case, for any continuous function, E lambda SF can uniformly converges to F of x0. But if S is less or equal, in this case, we have positive answer, in this case, negative. It was published in the well-known book of Solomon-Bochner, Fourier integral, in the 30s of last centuries. And then, after that, Marcel Ries introduces this means, and in general case, and so on. But if we consider the special case, now I begin to explain this phenomenon. That's a piecewise smooth function. What does it mean, piecewise smooth? The function is smooth inside omega, infinite many times differentiable function, for example, but has the jump on some surface. There is domain omega, and there is inside some subdomain D with very good boundary. This is D. And let's suppose that the function has the jump over there. It's very smooth inside, very smooth. For example, is equal to 1 inside and is equal to 0 outside. It's a very good function. And this surface is very good too, very many times differentiable. In this case, this critical index will be a little bit different. And now the main problem is not that, how smooth is the function, but not how smooth is this surface, the boundary of D. But the problem is where is this point x0 relatively to this surface D. The geometrical properties of DD, this property of convergence depends on the geometrical properties of this DD. And the simplest function, any function which has a jump over there and is smooth outside, may be written like f, like for example, j of x is integral of dd, dn. This fundamental solution multiplied by f of y d sigma y. Sigma is a surface measure, and f is some very smooth function which is defined on this surface dd. En is a fundamental solution. It's well known in theory of potential that it's a double-laid potential. It's well known that this function is very smooth inside, it's very smooth outside, and has the jump, and the jump just equal this f. I think it's well known, yeah? The jump of the function, which is represented by this integral, just on the border of the jump equals to f of y. It means that any piecewise smooth function can be represented by this integral. And if we consider this spectral expansion, we must consider, I would like to explain this Pinsky phenomenon from the 2 points of view, from the point of view of mathematical physics, of electromagnetism, and the point of view of just of pure mathematics. Yeah. First of all, we suppose that this surface dd, what does it mean double-laid potential? It means that there is electrical charge, and we suppose that it's oscillating with very big frequency. We consider in this case the integral I called A of omega integral d it would be better say a of omega and x f when omega tends to infinity. In this case, we expect that this integral will tend to 0. Why? It's well known because I can explain by this picture. If we have some on the segment AB, some function, integral is equal to this area. But if we multiply by sine, for example, the result will be something like that. And now integral is the difference between this area and this. And it's clear that this integral tends to 0. It's well-known theorem of Riemann and Lebesgue. Riemann proved it 150 years ago, maybe. Something 1850 maybe. And Lebesgue later for Lebesgue integral. Later, for the general surface, it was made by van der Corput. It's well known, the method of van der Corput. It was in the 19th century. How we can use this idea? This integral tends to 0 when omega tends. This is a theory of oscillating integral. And but sometimes it's not go to 0. I'll just explain. Let us suppose that it's surface dd. There is a point x, and distance between this y. And the distance is constant. In this case, this integral doesn't depend on omega. We can put this function over there, and it will tend to 0. Why it's necessary to ask them how to say, why we want this integral to go to 0? Because this E lambda f, E lambda SF, after some calculation, we can show that it's something constant lambda in the power n minus 3 over 2 minus s. S is this s. And there is some integral. If s is small, in this case, this value, lambda in this power, goes to infinity. And to compensate it, we ask this integral to go to 0. And now it's understandable. If x is in a very bad position comparing with d omega, in this case, it will not go to 0. Just the worst situation is if we have this circle and x is in the center. In this case, this r is constant. Integral doesn't depend on omega. The first theorem of Pinsky was to have the convergent spectral expansion of functions. It's necessary to fulfill this condition. It must be 0. In case, for example, whereas the function is constant here and constant here, it must be almost everywhere. It must be 0. Yeah, it was an unexpected result, and because of that, Kahan, a French mathematician, called it Pinsky phenomenon. In general case, if the situation is not like a sphere but some more complicated surface, we are in this point x. Here it looks like a part, like an arc, part of this circle. We need to demand that this integral along this part must be 0, just here. It's very good integral. There is very good, and more general situation when we try to integrate by parts this oscillating integral. We integrate this exponent in this every time lambda will go to denominator, and something additional too. This additional function may be 0. And to compensate this 0, we need to the function f must be 0 too at these points. If the denominator will be 0 with very high degree, in this case, f must be 0 with very high degree too. It depends on the not only on the geometry of this surface, but on the location of this point. For example, just this, the same situation. There is a circle. It's a worse point because here the distance is constant. Integral doesn't go to 0. But if you are here, everything is okay because it is very easy to show that this integral goes to 0 with very high speed. A little bit more difficult situation if there is this not circle but some complicated surface. But we can classify all the points. You see, it's impossible to say that it was the first work where the problem was discussed. The first was discussed by Maslov a little bit earlier, but only the absolute convergence. It was understandable from the point of view of geometrical optics, absolute convergence. But it's a much more complicated problem, phenomenon, Pinsky phenomenon, concerned with uniform convergence. It's, there is in proof in all the consideration there are big differences and it's much more complicated. And another thing, how we can interpret this result from a mechanical point of view. You see, you need to prove this theorem, you need to know some differential geometry, some topological properties, theory of oscillating integrals, method of van der Korput method, method of stationary phase, and so on. The best result about oscillating integral, they belong to Arnold, who proved some years ago a very good theorem about this, using the polygon of Newton polygon and so on, we can calculate the asymptotic of this integral. And what's the physical, mechanical meaning of this result? If we hit this, for example, plane domain, and this area is like this disk, in this case, in the center, there is a divergence. Maybe we'll hit from the another side with some shock in this area. The same sphere, the sphere with the same center, but a little bit bigger. Can we compensate the first shock so that there will be interference and the result will be very good? And some another additional shock and so on. And there is another result of Mark Pinsky and his, I think, colleagues and young pupils maybe, that you can try to do it, but it's impossible. You cannot compensate. Every time there will be the divergence. Especially the main important case when this is just the boundary. It's the influence of boundary to the convergence in the center. And the result is negative. If there is no if the condition of Pinsky will not fulfilled, in this case there will be divergence. It's necessary condition. Not enough, but it's necessary. Yeah. And you see, in this case, there is a new critical index, S. I call it n minus 3 over 2. It's very strange. It's for continuous function. It's what not continuous function, but it's less than in this case. But because this function is supposed to be very smooth outside this line of jump. And it means that if S is greater than this means tends uniformly or some compact to the function f. And if S is equal or less, in this case, this statement is wrong. Very interesting thing. In case n1, S must be just positive. Every time S is positive, or something like that. And S maybe 0 is greater than this. What does it mean? In case n, and in the case of n equals 2 or equals 1, there is no there is no influence of jump to the problem of convergence. It's really very interesting thing. In flat cases, there is no strong influence of this boundary to the. But in case when n equals to 3, there is such a connection here, and there is such a. And it was very detailed explained by Kahan first, and then by Michael Taylor. He wrote a special article which was published in Journal of Fourier Analysis and Applications about Pinsky phenomenon and wave equation approach. And using wave equation approach, he explained this idea. It was mentioned that I was not working as a mathematician some years, but 12 years ago I have got the article of 2 Italian mathematicians about the Pinsky phenomenon from the Central Blatt. It's a German version of Mathematical Review. And I began to study it, and after that I began again to study mathematics. I came to Pasadena, to Caltech, and I was very happy that Barry Simon supported me. And I have got some emails from Mark Pinsky. It was very encouraging me too. I'm very grateful, and because of that I began to study this problem and published some articles in Journal of Fourier Analysis and some others. Yeah. And I would like to use this opportunity to say my thanks. Yeah. Only because of that I became again, how to say, not mathematician, but the people who tried to prove some mathematical theorems. Yeah. And there is another explanation of this Pinsky phenomenon, mathematical explanation concerning with mean value formula. If we consider some, for example, this function. This function depends on R. It's a mean, something like mean value over the sphere. It's well known if this function harmonic is 0. But if the function is an arbitrary function, sometimes it's better. Let's suppose that f belongs to L2. In this case, it's impossible to calculate this integral because the dimension of this is n minus 2. Sorry, n minus 1. But this integral, according to Fubini theorem, exists almost everywhere for almost each R. And we can prove that it's a very interesting connection. If the function f has a very good spectral expansion, very good convergence, in this case, this function psi must be very smooth too. This is very strange. If we prove this theorem, we can get the Pinsky result too. Why? Let us suppose that psi is not smooth. In this case, there is no convergence. And what does it mean psi is smooth? Let's suppose that psi is 1 in some ball and 0 outside. Just on the border, it must be 0 to be this function continuous. Maybe now I just show some formulas from my presentation. Yeah, sorry. Yeah, that's Riess mean value. Marcelli is not Federico Riess. Yeah. I would like to add that the first result for Laplace, in the case when we consider Laplace operator, belongs to Carleman. And later, Levitan proved it for general elliptic operator of second order in 50s. You know, Boris Moiseyevich Levitan. And for the in general case, it was the same results were about the spectral function were proved by Lars Hermander. To prove these results, first his proof was not so precise, and result was not so precise. And he gives the lecture in, I don't know, maybe not correct pronunciation, Yeshiva University. There was conference concerned with the 70 years of the birthday of Marcel Ries. Marcel Ries, who was a teacher of Hermander. And to prove the precise result, he developed the theory of integral Fourier integral operators. Nowadays, they are used in partial differential equations, Fourier integral operators, but not so many mathematicians know that this theory was proved especially for this purpose, to study the spectral expansions and Ries means in 1968. Yeah. That is Bochner critical index. If the function is smooth enough, have mu derivatives, in this case S may be a little bit smaller, but the sum must be greater than this critical index. Yeah, and that's just example. When the function omega is, what does it mean piecewise smooth function? We have the very smooth function on the whole plane, on the whole, in the whole space, and multiplied by this indicator. And this is the result will be 0 outside and the same function inside. This is just one example of the simple piecewise smooth function, according to definition of Michael Taylor. Yeah, this is just fundamental solution. The specialists in potential theory, they know these functions. Yeah, in the two-dimensional case, it's just logarithm, and in n-dimensional case, these are in the powers denominator in the r in the power n minus 2. Yeah. 1 over r is a Newton potential, yeah? It's well known as a Newton potential. And this PF, this is double laid potential, this function has a jump just over there. Yeah, you see, when you come to the this border of the domain D, from the inside, in this case, the value will be so. And if we go from outside, PF minus f of a over 2. And the difference is just f of a. It means that the jump is just f of a. And because of that, it's enough to consider just only this function as a double-laid potential. Yeah. And then we can use the green function. It's a kernel of the resolvent and the point lambda 0. And it's well known that green function looks like a fundamental solution. And the double-laid potential we may use like this integral. And now it's almost understandable how to prove these theorems. We consider this spectral function. I again would like to say that the best result for Laplace operator were proved by Carleman in 1930s, in 1950s by Levitan, and some others too. And all of them used the Tauberen theorems, Tauber type theorem. Carleman first was, how to say, uses this theorem to prove his results, and he studied the parabolic equation, and Levitan wave equation, and Hermander Fourier integral operators. Yeah. It's a very simple consideration. That's the main formula. You see, this spectral function of green function is like this. It's Bessel function. Maybe it's not so interesting too. Yeah. Because of that, I decided not to show this PowerPoint, but just to explain by this blackboard. And this is the final result. You see, just this formula, lambda in this power. Now it's understandable why n minus 3 over 2 is the critical index. When s is equal to that, it's 0, f equals just to this integral. But if 0 and this integral is not 0, there is no convergence. But if s is greater than this one, it goes to 0, just to the value of f. But if s is less than 0, it's possible to find the points where it converges to 0 very fast. It depends on geometry of D and of the location of the point x. I explained it. Yeah. This is the same formula, and this is what I did say. This is new critical index. And I think it's understandable. Yeah, and well, we can use some consideration concerning the Pinsky phenomenon. We can choose the f so that this integral must to go to 0 just when you are integrating over some very bad part of the boundary D. I'll explain it on the next picture. Yeah. That's just integrating by parts. This idea belongs to van der Corput.
These formulas are also hot when the boundary of D is not connected.
Just the same. In this case, the function f is the finite sum of some different function fk. And you may consider, I said about another theorem of Mark Pinsky, if we have the sum of these functions, they cannot compensate this divergence. The divergence will be with different phases. It's a very complicated lemma, showing that they have the same degree, how to say, when they go to infinity, for example. Yeah. 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 This very interesting lemma in your article, in analysis, global analysis, I think, analysis of global analysis. Yeah. Yeah. And I didn't say about my results, they are not so interesting, but some generalization of results of Mark Pinsky for some more difficult, more complicated operators, more difficult agents, domains, and so on, but the same result. Yeah. And you see, after integrating by parts, in denominator will be the function omega. You see, omega of xy. Omega is that's the definition of omega. You see, what's the bad situation when x minus y multiplied scalar product by tau of y if it's 0? Just this picture. There is x, there is y, this x minus y, and this is tau. Just in this case, this angle is pi over 2, in scalar product is 0. It's a worst case. That's the center of this circle. And omega is 0, omega is in denominator, and to compensate it, we must suppose that f is 0 at the same point. This is just the result, this is just Pinsky phenomenon. We need to take this f, which is 0 at the same points where omega is 0. In case of circle, all these points have this property, you see, because this is tau, this tangent vector. And this is x minus 1, x just on the top, x minus y multiplied by tau. And it's 0. Scalar product is 0, yeah, because they are orthogonal. And this omega is, you see, it's in the denominator. It's I tried to explain the idea of the Pinsky phenomenon here. There is a problem, a connection with localization too. What does it mean, localization? In case n is 1, when n is equal to 1, there is a Riemann theorem of localization. If the function is very smooth near the point x, the problem of convergence depends only on the behavior of this function f around this in some neighbors of x. It doesn't. Maybe the function may be very bad far from the point of x. This is a result about the localization. It doesn't matter. Just the same in case when n equals 2. It's understandable from this formula. But in case n equals 3 and greater, the function f may be 0 near the point, but however there will be divergence at this point. Because the function is very bad far from this point x. There is no localization. And this is a consequence of Pinsky phenomenon too. And sorry, I very often repeat your name, Mark, but it's necessary to explain all these results. And you see, now we consider this new mean value around the sphere of radii r. Yeah, we introduce it. And I'll show just one formula which looks to me very interesting, a little bit strange. After some calculations, I explained this. This additional formula. If this function have additional m derivatives, in this case we can take a little bit smaller too. No, it doesn't matter. Just a second. This formula too, or maybe this formula. You see, on the left side is the mean. This is integral over sphere of radius r. On the left. On the right side, there is some integral where is spectral expansion. Only in the point x. On the left side is integral over this circle, and on the right side, only at the point x. There is no connection between the values of function here on the left side. To calculate the left side, we just have the. I'll show this integral again. You see, we just integrate along the sphere of the radial error, not inside the ball. Again, on the left side, there is only the values of A on the border of this ball. And on the right side, only at the point x. We can change the function. On this, for example, we can change function inside this ball, but do not change in the on the border on the sphere. And in this case, left side will be the same, and it follows from this formula that the right side is the same too. It's a little bit strange, and it explains the Pinsky phenomenon too. It's necessary to this function SRA. If there is a convergence, it follows that SRA is very smooth. Is continuous. Vice versa. If SR is not continuous, in this case there is divergence. And let us suppose that the function is 0 outside. This value must be continuous. It means that this integral is 0 because the function is 0 outside. And to be continuous for this function, it's necessary this integral must be 0 too. This is Pinsky phenomenon. Yeah. And Pinsky proved it in general case of Riemannian manifolds, of some special Riemannian manifolds. How to say, whether the some symmetric and we call them harmonic sometimes, harmonic Riemannian manifolds. You can find the properties in the special chapter in the book of Helgason, differential geometry and symmetric spaces here. One of the last chapters here. But I explained just in the case of Euclidean spaces, the results are the same. I can explain some more, how to say, some other details, but I think that they will be not so interesting. And because of that, that's some results which were published. When I got these emails from Mark Pinsky, I changed something and published these articles. That's acknowledgement, and that's all. Thank you.
Any questions?
One question. What do you mean Laplace-Beltrami operator?
Yeah.
You mean on plane, an example?
No, in plane just Laplace operator.
What operator is it?
Laplace? In
Laplace-Beltrami, you said?
Laplace-Beltrami on manifold. But Riemannian manifold.
The same.
On the sphere, for example, on the torus. But if you consider Rn Euclidean space, it's just Laplace operator.
Because we mean another operator in complex.
It's a d plus d different d's, yeah. You know that. It's only one. On any Riemannian manifolds, there is only one Laplace Beltrami operator. Just in flat case, it's just Laplace operator, yeah. Because of that, there are some these mean value formulas. How to say? If the function has a very good, convergent spectral expansions, it means that the value of these functions are very good balanced. Just the value, the center of some sphere in Riemannian sphere, just in the center of sphere is how to say, is connected with the mean value over the sphere. The value in the center, yeah, is how to say it. There is a connection between value in the center and the value of on the border, yeah, but only for Laplace operator. In general case of operator of second order, there is some additional terms, and the proof became very difficult. Only elliptic operator, yeah, only.
Spherical harmonics.
Yeah.
Laplace spherical harmonics is a dual case. We spoke about the spherical harmonics is a positive curvature and negative Laplacian negative curvature. It's the exact same theorem in all cases. Fourier partial sum convergence, even only if the smoothest index is at least n minus 2.
Yeah.
Over the cases.
Yeah. But I just would like to say, as a final remark, that the main idea is a connection. If we consider the piecewise smooth function which has a jump on some surface, there is a connection between the geometry properties of this surface and the properties of convergence at some point. It depends on the location of this point, comparing relatively to this surface. And this is the discovery of Mark Pinsky. And I'm very happy that you are here. Yeah.
Any more questions?
Interesting for me about set of such kind of things.
Yeah. Yeah. Well, I published this article in the Journal for Analysis and Applications. We can this omega equals to omega 1 plus omega 2 plus omega 3, and each omega depends on the location of this x comparing with this surface. It depends on degree of this special function like this omega, but not this omega, another function. And here the convergence is not bad. There is a little bit worse, and there is the worst situation. How to say? We can continue. It depends on number n, number of this omega. We can classify all these points, but it needs too much time to explain it. Yeah, but there is some results. Yeah, and I think that Professor Ashurov maybe will tell something about that. I don't know. He published it with his pupil. Almaz. Now he's in Canada. He was going to come, but he didn't. Yeah. Almaz.
Measure of this set is 0 or not?
Oh. Some of them have the measure 0, but not all of them, because this omega, yeah. No, it depends on number n. Yeah, but the worst point, they have the measure 0. But some points are, just one example. Let us consider the torus. The bad points are, this is just the circle which is in the center of this torus. Yeah, and if we consider this ellipsoid, these points are not good, but these two are the worst. And the measure, you see, the 0, the dimension is 0, this dimension of 1, and so on. It grows, this dimension. Yeah, it's a normal thing in the theory of oscillating integrals. Yeah, yeah. The behavior of this integral comparing with the location of this point here. It's impossible to construct the whole theory from the beginning, yeah. Everything was ready, but it was necessary to look from another point of view. Sorry.
Any further questions? Okay, then let's thank our speaker again.
Yeah. Thank you.
Back, and it's a great honor and privilege to have Barry Simon to give our next talk. The title of the talk is Semi-Classical Limit of Thomas Fermi Theory 40 years later. So please.
Okay, so let me begin by apologizing for not having spiffed up the slides. So it says where I first gave the talk. I currently have, I've never learned how to tech, and I currently have a glitch in my secretarial services, so it was not easy to get someone to fix it, so I apologize for that. And some things will say this year when it really means last year, so I apologize for that in advance. Right, I reached the age where I tend to think of anniversaries, and it was now 40 and a half years ago that Lieb and I did our work on Thomas Fermi, and people don't really know, not all people know the details, and it's an interesting story. So I'm going to both tell you about the mathematics and also some of the history. So Elliot and I started our work in the fall of 1972. I had met Elliot 2 years before when he was a professor and I was a student at the famous 1970 Les Houges Summer School, and we were both at the IHES in Bure-sur-Yvette near Paris, at least in the fall. And by the time the paper was finally published, it was 1977, but most of the work was actually done in 72, 73. And I believe the key step when we had a theorem, it was going to be something interesting, although we had some results before then, was in March in 1973. I left for CNRS in Marseille, but Elliot stayed, had a nice apartment in Paris. I came up to stay with him in Paris, and we pulled the Coulomb tooth, the poison, not Poisson, the poison Coulomb tooth. And so it's now roughly 40 years since the work was done, which when I was the age of many of you here, I thought, I just realized, for example, the other day that I'm about the age of Value Bogman when he retired, and I thought of Bogman as being older than I don't know what. So, right? We all get older, at least if that's the good news, if we all get older. In the fall of 72, as I said, we were both visiting IHES. Elliot was 40 at the time. He had recently been hired by MIT. He'd been in smaller institutions before then. He had done this work on 6 vertex models in statistical mechanics and the so-called entropy of square ice. It made a big splash, and he wound up in the applied math group at MIT and was visiting IHES. I was 26. I had just been promoted to tenure at Princeton 3 years after my PhD, but I was a sluggard in my year because Charlie Pfefferman had entered graduate school when I did. He was 16. He finished the same time I did, but he got his tenure after only a year, and he was immediately a full professor. I mean, Charlie, and with good reason. I mean, if one understands what he did in that year, it's well deserved. Elliot and I started talking a lot because we were, we're at this institute every day, and early on he suggested we should look at Thomas Fermi limit theory, which he felt should be exact in the large nuclear charge limit. And as we'll see, that's true even. And I had been a physics undergraduate at Harvard, taken a lot of math courses, and the training I got at Harvard was incredibly formal. Paul Martin talking about Green's functions in quantum mechanics, Schwinger talking about. And so I would never have seen anything like Thomas Fermi theory at Harvard, because that was too real for the theorists at Harvard. But in my junior year, I managed to corner George Mackey and in the hall one day and ask him if there was any place I could go. I knew what I wanted to do. I wanted to do rigorous physics, but it certainly didn't exist at Harvard, where they said, theorem? What's a theorem? Or even worse, theorem? You want to worry about theorems? And he told me about Arthur Whiteman, who I'd never heard of. And it hadn't occurred to me to apply to Princeton. Princeton was not really on my radar. I probably would have wound up at Berkeley working for Wichmann if I hadn't run into him. But I did. I wound up doing my thesis with Arthur. Arthur passed away last January, meeting a year ago, January, at age 90. And I have a huge debt to him personally, and I think the mathematical physics community also has a huge debt to him. In my first year at Princeton, I took a course from Arthur that was called Intermediate Quantum Mechanics. I believe no other course in the United States, given at the time with that name, would have done anything like what Arthur did. Right? He proved Kato's theorem about self-adjointness, and maybe Yost in Zurich or Turing in Vienna might have given courses like that. In fact, Turing's book is not so different. But in particular, he spent a week on Thomas Fermi theory and included Teller's theorem, which I'll say more about later. But Teller's theorem says, in this Thomas Fermi model, atoms do not bind. So Elliot kept telling me how wonderful Thomas Fermi was, and I said to him, it must be wrong. It can't really describe matter, because we know that molecules do form in nature. And even for large, I mean, you know, uranium oxide, you can bind. And Teller's theorem says Thomas Fermi didn't describe that. So Elliot went home. Next morning he walked in and said, Mr. Dalton's hooks are in the outer shell. For those who don't know, Dalton is the one who invented the shell model of chemistry to explain how molecules form. And his point was that chemistry takes place in the outer shell of atoms, and Thomas Fermi theory, which involves the bulk of the atom, is describing the core. So the fact that it doesn't describe chemistry should not bother me. Of course, that does mean, you know, there's even been a Nobel Prize now in chemistry for, a long time ago, in fact, for density functional theory. They love density functional theory. Thomas Fermi is the simplest. It's the grandfather of all density functional theories. But if you want a density functional theory that describes chemistry, it better not just be Thomas Fermi theory. So Teller tells you that. So Teller's theorem is actually irrelevant to the z going to infinity result, although it's exceedingly useful. Well, we actually proved Teller's theorem in our paper, because Teller didn't really have a proof. I'll come back to that. Because having told him about Teller's theorem, Lieb and Turing, a couple of years later, actually used Teller's theorem as a key step in their proof of stability of matter. So once we convinced ourselves that Teller's theorem was not a problem, we started working on developing what was needed. So what was needed? Well, the first thing one needed is to prove existence of solutions of this Thomas Fermi equation, because we're going to want to prove the solutions. Look, I guess you wouldn't need solutions just for the energy result, but we actually wanted densities too. So you need to know this equation has solutions. We needed to know that in the large z limit, where there was suitable scaling that I'll describe, there was a semi-classical limit, but we knew all along that there was a problem. We're interested in an atom where as z goes to infinity, you have this extreme Coulomb singularity, and we knew that was going to be a hard issue, and so we were going to first do it when you cut off the Coulomb energy, and then we needed to figure out a way of dealing with this Coulomb singularity. I already told you this. So we settled the main issues except for the Coulomb singularity. I went from Marseille to Paris. Elliot had an apartment. We banged our head for several days. I actually visited him. We figured out how to solve the Coulomb problem. So now I want to tell you a little bit about Thomas Fermi theory. So Thomas and Fermi it's actually named after the people who invented it, a counterexample to Arnold's principle. It was developed independently by Thomas and Fermi. Thomas was at Columbia University at the time. Fermi was in Rome, and this was in 1927, which was slightly over a year after the Schrödinger equation was actually written down for the first time. So it was very early on. They wanted to describe, they said, we want something where we're going to describe a situation where you're semi-classical and the main thing that matters is not the wave function, but just the electron density. So they had in mind there should be an electron density rho. The model they had was, by then, they very quickly had this idea of what's called the Fermi sphere. You put in lots of electrons till a Fermi energy, and the energy of the kinetic energy of the electrons is determined by the momentum of the electron at the top of this Fermi surface. A little more complicated, but that's basically what it is. The density should be the volume of this Fermi sphere. The Fermi sphere lives in momentum space. And so the kinetic energy should go like the 2/3 power of the rho. And their basic idea was the top of the Fermi energy should be, C should be a fixed energy called the Fermi energy. And what that's telling you is the potential energy is, of course, given by a combination of the underlying nuclear potential, not a very strong laser, I guess, at the bottom line. And their notion was, their basic equation was the total energy should be the Fermi energy. So this Fermi kinetic energy divided by 2m minus the potential energy should be a constant, except, of course, at points where there are no electrons, right? You basically put in electrons to the top of the C if, in fact, the potential energy is already above where you are. You don't put in any potentials. This is in the end, and when we start writing down mathematics, it's going to be connected with a Lagrange multiplier and the fact that something's an inequality. We'll talk a little bit more about this. But this was their basic equation. And they therefore got a self-consistent integral equation. Namely, you take this energy, which we saw was rho to the 2/3, and it's given in terms of rho by this equation. This is the so-called Thomas Fermi integral equation. V is exactly the Coulomb energy. This is, of course, very difficult to deal with. This, first of all, the positive part, which is a little bit bothersome. But in addition to the positive part being there, it's an integral equation. Physicists don't like integral equations. They like differential equations. But since it's a Coulomb energy, you could, in fact, look at the Laplacian of the potential. The Laplacian of the potential was the density rho, which if you work out is in fact phi minus, this is phi, it's phi minus phi naught to the 3/2 power. So this is the differential equation they wrote down. They then talked about solving it in radial coordinates. They were interested in atoms at that point, and so they looked at the spherically symmetric case. And there was lots. There's a fairly substantial literature in the 1930s on this Thomas Fermi equation, because it's, of course, impossible to solve the Schrödinger equation when you have more than 2 electrons. In fact, even 2 electrons took till the 50s before you got good variational wave functions. And I've been talking about multi-centers in general to describe molecules also. And so you then get your ODE actually becomes your PDE becomes an ODE because of spherical symmetry, and that's called the Thomas Fermi ODE, which they got a lot of information on. When we began working, there was only one result that I'm aware of, rigorous result about Thomas Fermi theory. It was only done in 1969, over 40 years after they did their work, and only a few years before Elliot and I did our work. It was done by Hille, who by then was 75 years old. So it comforts me to know you can still prove interesting theorems when you're 75. And he used ordinary differential equations and proved existence and uniqueness of solutions of this spherically symmetric ODE. And of course, before then, people had done numerical, and as I said, there's lots of numerics. And he also rigorously proved the asymptotics of this solution, that it was a constant. He even knew the constant, I suspect, times x to the minus 6. We'll talk about that a little later. This was actually already found by Sommerfeld at the level of physicists' arguments in 1932. So for us, the key was to use a different approach, which Lentz wrote down in 1932. Lentz was, in fact, Ising's thesis advisor, and the Ising model was named after Ising for his thesis. It sometimes was called the Lenz-Ising model. And of course, Ising had both a wrong statement about no phase transitions in 2 dimensions and solved the trivial 1-dimensional problem, but probably his name appears in the physics literature maybe more than anyone else's name but Schrödinger and Heisenberg and Newton maybe. And Lentz defined the Thomas Fermi energy by the following form. If the average momentum, if the average energy goes like rho to the 2/3, then to get the actual energy, you have to multiply by the number of electrons. So you're going to get rho to the 5/3. So the first term is the kinetic energy term. The second term is due to the interaction between the electrons and the underlying potential of the nuclei. And the last term is the Coulomb repulsion of the electrons with one another. And we think of the Thomas Fermi energy as being the minimizer of this functional. So we don't think of it as there being either an integral equation directly or a differential equation. It's rather a minimizer of this problem, which turns out, of course, by the Euler-Lagrange equations for this energy to be the same as the Thomas Fermi. But we really want to think of it as a minimizer. And the minimum energy is the TF energy. And the first step in proving the quantum limit is to prove that the minimum. So the first thing we want to prove is that the minimum energy of a quantum system of nuclei and electrons, as z goes to infinity, converges to Thomas Fermi, although as we'll see, you want to scale everything. And as a bonus, it turned out we could get that the densities converged by some magic that I'll talk about, because the energy is convex, and so if convex functions converge, their derivatives converge, and the derivative of the energy turns out to be, with respect to changes of v, turns out to just be rho. So we got convergence sort of for free. Now, I went to Beer. I regarded myself as an expert in linear functional analysis. Reed-Simon Volume 1 had just appeared. But I didn't know much about nonlinear functional analysis, which was the issue here. Fortunately, many of the tools we needed actually, which is true even today, of nonlinear functional analysis are in fact from linear functional analysis. And as a graduate student at Princeton, I'd taken a course from Shavkat. He has a book called Lectures on Analysis or something like that, a 3-volume book that Marsden and others, and those were notes from the class that they were in and I was in also. And he had talked about some minimization problems. So I knew what you needed to do. I knew what tool you needed. I now know, although it's only recently that I've learned this tool is called the direct method of the calculus of variations. And it's that you get minima by compactness and lower semi-continuity in the right topology. That's the mantra of getting minima. And the point is you need to use a weak topology to get compactness and then use the Banach-Alaoglu theorem because norms are generally not weakly continuous and therefore not weakly lower semi-continuous. Now, the nice thing that if you ask who's now the biggest world expert on some of the ins and outs of using the direct method, it's presumably Elliott Lieb, right? There are all these things when you have symmetry, when you don't have symmetry, how to handle the lack of, that's all. Elliott's the big expert, and I'm the one who taught him about the direct method of the calculus of variations. We proved the existence and the quantum limit theorem, and we got the quantum limit theorem in March, as I told you. We wrote up an announcement and sent it off to Physical Review letters. I actually, a few years later, was used to calling this Physical Review lottery rather than Physical Review letter because the refereeing was so uneven. I believe the average quality of the papers I've had rejected by Physical Review letters is at least as good as those I've had accepted. If there's time, you can ask me a question afterwards, and I'll tell you about a wonderful referees report I got. I'm going to tell you about a not so wonderful one. And the paper is actually part of the story because the paper was rejected. The report stated, and I only paraphrase, I don't have the actual report anymore. This is one of the worst papers I have ever seen. It is a sequence of unproven assertions. That part is correct. It was an announcement. We made statements and didn't prove it. Many of which are obviously false. For example, the authors assert the Thomas Fermi density rho is C super infinity, which would make rho identically 0, 1, or infinity, depending on the value of C. The referee's report also got some of the physics wrong. So Elliott insisted that we not complain that he was incompetent mathematically and in our complaint, but very soon after our complaint was received, the paper was accepted. I later heard a rumor that they'd sent it to Freeman Dyson, who got at least as big a kick out of the C super infinity as you did, and told them to accept it. It took a while to write because Elliott, after we were both together or not so far apart, Elliott returned to MIT, I was in Princeton, and there were some issues. We wanted to discuss solids. The final paper was 50 pages long, not because the proof is so complicated, because we put this other stuff in that I think is interesting. But we then lured Elliott to Princeton, where he's remained, and I haven't to this day, and things went faster. And we submitted it to Advances in Math, which solicited the paper and then proceeded to sit on it for 2 years until we threatened to withdraw it, and then they published it. So that's why it was 1977 before the final paper appeared. So now I want to spend the rest of my time telling you a little bit about the details of the proof. No, not so many stories anymore. So as I said earlier, is there by any chance another laser pointer here so I could... No, okay. So you take the nuclear potential, has charges Z at centers capital R, J, and this, as I told you before, is the Thomas Fermi density. We want to first prove existence, that is minimizers, which doesn't always happen. We'll see in a second. So you look at the set of positive rows, functions rho, And in order for the Thomas Fermi energy to make sense, you want rho to be in L5/3. And because we want a total density, the number of electrons should be either Z in the neutral case or N in general. You want to have N electrons. Good, thank you. Because you have N electrons, you want the integral of rho to be N, so you want it to be in L1. And fortunately, if rho is in, because the Coulomb potential is in L infinity plus L5/3, in both these terms, there's no problem with the integrals converging. So if you look at positive rhos with this condition, the Thomas Fermi energy is defined. That's what I just said. And the first theorem we proved is the following, that for any capital N, that's supposed to be the number of electrons, there's a unique minimizer rho that minimizes this quantity subject to rho being less than or equal to N, not in general equal to N. And this follows fairly easily because the function is lower, the energy E is lower semi-continuous. The set of, you easily see that knowing that E is less than some fixed large constant actually puts, bounds the L5/3 norm, and the L1 norm is assumed to be bounded. So you're looking at a compact set in the right weak topology. So that gives you existence, and the functional is strictly convex. That gives you unique minimizer. But the problem is that it's not weakly closed if I set the integral of rho equal to N. You can take weak limits and some charge can march off to infinity or pop up at the top. I think it can. Well, it certainly can march off to infinity. So in fact, it's only rho less than or equal to N, and that's a good reason for that. Because if N is bigger than Z, if N is less than Z, the minimizer, in fact, has equality. If N is bigger than Z, the minimizer still has the integral of rho equals Z. Unlike, this is a variant of what Tellerlade proved. Not only does Thomas Fermi not bind molecules, it doesn't bind any extra electrons. There are no negative ions in Thomas Fermi theory, which is a much weaker statement than, by the way, it's a very interesting fact of nature that no atom is known that will bind more than one extra electron, but there is nothing close to a proof of that fact. Right? It's a little better than, we know that it doesn't bind more than order little o of n, and I think it's little o of n to some power, but I don't even remember what the power. But we don't even know it binds less than 1 million extra electrons. There's no proof of that elementary physical fact. But of course, physicists don't understand it either. It's just an observed fact. And I'm not going to try to give you anything of the proof, but it basically used some potential theory. It used the fact that this Thomas Fermi density phi really wants to be in the neutral case. Well, it wants to be always, the density needs to be rho, and anyhow, it uses some potential theory. I'm not going to try to give you the proof, I think. We also proved that away from the points Rj, rho Tf is C super infinity. That was the complaint of the referee. In the region, at least in the region where rho Tf is positive, if in the ionic case, the rho has compact support, and there's then it's only, I think, C3 across the region where you go from some electrons to no electrons for good physical reason. And we proved Sommerfeld's asymptotic formula. Here's the exact theorem, that in the neutral case, the density, that's wrong, times, that should be absolute x to the +6, converges to 27 pi to the -q And again, the proof used some subharmonic comparison theorems, and there was nothing close to a proof even in the physics literature of this in the molecular case. All the proofs depended on using the ordinary differential equation and analyzing it. And we proved Teller's theorem. That's the theorem that says if you look at L plus K L plus K nuclei, then the energy is always bigger than what happens if you separate it into two parts. So this is an assertion that right, with molecules, if you put two of them together, you get extra energy. You get, the binding energy is bigger. This is a binding energy. This says there's no extra binding energy. And this means that in Thomas Fermi theory, matter is obviously stable because, right, a bunch of molecules always has bigger energy than a single atom times the number of atoms. That's exactly what you need for Thomas Fermi in essence, for stability of matter. Yes. And the proof, Teller sort of got close to a real proof, but Teller needed the existence of solutions. He assumed that there existed solutions to the Thomas Fermi equation, even though no one had proven that, because physicists know it has it. You look at the molecule. And we want to see what happened as z goes to infinity. So for us, one of the key result is what does Thomas Fermi look like when you make z large? And the miracle is, and I want to analyze the separate terms here, so I'm going to give them names: the kinetic energy, the attraction, and the repulsion. And this one is multiplied by z, and we want to fix, of course, the density, and we're going to make an ansatz. We're going to suppose that when I increase z, the solution just changes by scaling an x and multiplying rho by a constant. So if you make this ansatz, because you want the integral of rho z, we're going to look at the neutral case, for example, to be z, then, right, the number rho z is going to be, when you do the scaling, z to the alpha, right, that comes, right, there's a z to the alpha that it multiplies the integral of rho, and then from undoing the scaling, there's a z to the minus 3 beta. So the number of electrons gets multiplied by z to the alpha minus 3 beta. You want neutrality, and so you set that equal to 1. And you then play around with the individual terms, and they have different powers. You decide that in order for these two to scale the same way, you have that equality. You also have that equality. You can solve for alpha and beta. Alpha is 2, beta is 1/3. All of them scale like z to the 7/3. So the net result of this little calculation is that the minimizer for z equals 1 gives you, by multiplying by z to the 4/3 in front, no, z squared in front, multiplying, scaling in by z to the 1/3 gives you the minimizer for charge z, and the total energy grows like z to the 7/3. And if you want to know the same thing for molecules, you've got to look at molecules as the charges go in. So another way of understanding why Teller's theorem is not related to the true physics is if molecules bound in Thomas Fermi theory, you would gain energy by pushing these molecules to a distance which decreased like z to the minus 1/3. And if anything, as charges grow bigger, the size of molecules grows bigger, not smaller. So that's why Teller's theorem holds. If you try to push them in, the cores interact because Teller's, and you get no binding. And the theorem, oh, and then you can, right, this is just a statement about, that I told you about how with fixed little charges, Z and R, if you multiply everything by Z, the charges by Z, the number of electrons by Z, and you scale the R's by Z to the minus a third, then the energy just gets multiplied by an extra Z to the 7/3, and the Thomas Fermi density, equilibrium density, just goes like Z squared. And we made an amusing observation that helped explain why you get this x to the minus a 6. It's the unique power that's invariant under the scaling relation. But it's important to understand that one of the morals you learn from this scaling is when you do quantum mechanics in a large Z atom, the natural scale is Z to the minus a third. You want to take your microscope and look at it on this Z to the minus a third scale. So if, as we're going to do in a second, we're going to use a Weyl-Dirichlet-Neumann type decoupling, that's how Weyl proved his semi-classical limit theorem, you need to put your boxes shrinking like Z to the minus a third, which is what we did. So that's what I just told you, really. And so now what I want to do is I want to look at the real honest-to-goodness quantum system. This is the kinetic energy. This is the attraction to the nuclei. This is the repulsion of the electrons. I guess that Q is a J. And you want to look at it. And your wave function has values in 3n variables, and they're not numerical values. If you want to take spin into account, you've got to take c2 to the n. Spin is sort of trivial in this setting, to add or not add, and I probably will ignore it at the rest of the talk. And the quantum energy is, by definition, the inf over all phi, which are antisymmetric in these combined variables. And that's really what physics tells you in a model, a non-relativistic model. Of course, as Z gets larger, relativistic effects become important. You can't actually produce Z's of more than now, I think, 120 something, and one doesn't believe. But if you ignore all that, as a mathematician, this is the model of a large Z molecule. And what our theorem says, it's the biggest, it's the big theorem in the paper. It's the one that when we could prove it, we said, we have something that should be published in PRL, is that the quantum energy, if you scale the nuclear distances by this amount, and multiply all the, and make n grow like Z, you divide the quantum energy by Z to the 7/3, you get just the Thomas Fermi energy. So Thomas Fermi theory, in this sense, describes a large Z atom. Now, we got the leading term, which is Z to the 7/3. This became a little industry. There were and the results I'm telling you here are much harder. Well, Z squared isn't that much harder. There's a Z squared term, which is called the Scott correction. And then there's a Z to the 5, and the Scott correction was obtained by Hughes and by Seedtop. And then the next term, which is oscillatory, is by Z to the 5/3. That's a theorem of Pfefferman and Zako in about 6 papers that total over 1,000 pages. And that's not because they looked at other things, it's just the details of the proof of that result. And you need to take things, right? This is just telling you that you should take the number of electrons to grow like a constant multiple times z. Of course, if lambda isn't rational, there's a small problem, and I should take the integral part. It's still true, but I'm not worrying about that. And the physically interesting case is lambda equals 1. And electron densities, we had them for 1, and it turns out to be an easy consequence. It's magic, because the one particle density is, for the quantum system, done with this scaling, converges weakly in the L infinity sense to, in fact, the Rho-Thomas Fermi density. That's the theorem. And it's a simple corollary, because if you change this potential, you take the Coulomb potential and you replace it by this, then this quantum density, by looking, is just the derivative with respect to V, a change of V of this. And this is this energy is a concave function of V. Convex, concave, I'd have to, it's concave, probably concave. Well, maybe I'll say in the next slide. It says convex, but in fact they're concave, I think. What?
Concave.
Yeah, it's concave. But till you look at the negative, it's still true for, and it's a fact, it's a miraculous fact that if you have a sequence of convex functions that converge, then the one-sided derivatives of that convex function, if the limit function is differentiable, converge to the, there's a derivative missing. Boy, this is really awful. That's a terrible typo. That should not be Fn, it should be the derivative of F. Sorry. And we didn't have to do any work to prove the limit theorem modulo the Coulomb thing, because someone had essentially already done that. So at the time we were talking about this, Weil in some sense had done it when he proved his eigenvalue, but if you want to do it for minus h bar squared over 2m, Laplacian plus v, v fixed, h bar goes to 0, then in fact the number of eigenvalues, the binding energy, they're all given by quasi-classical formulae. This was proven when v was a nice function, probably continuity is enough. When it's negative and it goes to 0 and infinity rapidly, independently without actually knowing of each other, by Martin, Robinson, and Tamura, and also Biermann and Borsov, although when we wrote the paper we didn't realize that, and I had forgotten it when I made this slide. But lots of people had independent. It's a very simple extension of the Courant-Hilbert proof of Weil's theorem, actually. The idea is it uses Dirichlet-Neumann bracketing, and given that I have 5 minutes, I'm going to assume you know about Dirichlet-Neumann bracketing, but the point of Dirichlet-Neumann bracketing is that if you take minus Laplacian plus v and you partition space into cubes, if you put Dirichlet boundary condition on all the cubes, then the energy goes up, and if you put Neumann on all the cubes, the energy goes down. That's the magic of quadratic forms. And so that's what you do, and then in each box you replace all the potentials by their minima. If you want to get a lower bound, so you use Neumann boundary conditions to place them by a minimum, and then you place them by the maximum and put Dirichlet boundary conditions. You then do a quasi-classical calculation for constant potentials, where you're just counting lattice points. And that way you get these results very easily, except for one small problem. You get this bound, as I told you. And so if you replace z over absolute x by this, where v is continuous and bounded, then the same theorem with boxes lets you prove a Thomas Fermi limit theorem, except when doing the proof, you have to scale the boxes in by z to the 1/3. You then get, you put the boxes with Dirichlet boundary conditions in to get an upper bound on the limb sup. You then get a bound on the limb inf by putting in Neumann boundary conditions. And then by taking the box sizes to 0, in these limits, you see the two objects become the same because V is continuous, and therefore you get that the limb sup and the limb inf are the same. It's really, and it's given by the quasi-classical formula. It's a very simple argument. This is a small problem. Suppose, in fact, the electron collapsed. Quantum energies actually grew faster than 7 to the 1/3. That could happen so far. If that happened, we wouldn't see it, because the only way that could happen is if the electrons fell in faster than this z to the 1/3 rate. And there'd be infinitely many electrons in the box that happen to contain the nuclei, the boxes, the multinuclear case, that happen to contain the nucleus. And we can't, you know, with this argument, we can't say anything about those boxes, because the argument was to replace V by its minimum in one of the bounds in the box. And the minimum is minus infinity. So we knew we had to worry about the Coulomb tooth, how to handle the Coulomb tooth. And what we realized in March were two things. One is that we only needed to solve a one-body problem rather than an n-body problem to control the Coulomb tooth. And our idea was the following. Take the Coulomb potential and cut it off at some short distance. And we fix this cutoff R. We look at the same n-body Hamiltonian, except we're going to look at this with this particular Hamiltonian. We still scale with z. There should, in fact, be a z to the 4/3 in there. I apologize for that. And you put an alpha, which is going to be a small number, but a fixed alpha in, and you still minimize. That's a one-body problem. Suppose we prove that for this one-body problem, the binding energy as z goes to infinity as delta, which is the, right, this is the R, the place you put the cutoff, is a small amount times z to the minus 1/3. If you can prove that as this, you pull the Coulomb tooth in, this total binding energy goes to 0, then it's not hard by using variational approximation arguments to show this Coulomb core doesn't matter. Because you've proven it makes an infinitesimal contribution on the z to the 1/3 scale in this model. Now, of course, you still have a Coulomb problem here, but it's a one-body problem. We know how to solve one-body. I mean, it's a one-body problem. It's non-interacting electrons. You're looking at n electrons, but they're non-interacting. The minimum energy is just twice, because there were two spin states, the sum of the negative eigenvalues. So what we actually proved was a following bound on the, in terms of these parameters alpha and z and r. Doesn't matter what it is, the important, well, it does matter. I'll talk about that in a second. And, well, yeah, I'm talking about you now. You put in these values and you'll discover this is, because all these terms, if you put in the right values, happen to behave like z to the 7/3. You use that z to the 5/6 times z to the minus z to the 5/2 times z to the 7/3, right? Everything works out great. And that gives you the whole result if you can prove this bound. Now, Lieb and Tiering faced the same problem a couple of years later, bounding the sum of the number of eigenvalues. If we had their theorem, we would have been done. We could have just used this theorem. It's easy then. But we didn't have their theorem. So we used our bare hands. And the way you use the bare hands is all we really used in this argument were two things. First of all, because we've cut off the potential at this distance r, and there's a angular momentum barrier for each fixed r. In fact, this is what you get. There's a cutoff. There's a maximum L where you can have any bound states, because the Coulomb barrier is just bigger than the cutoff Coulomb potential at because you put the cutoff in. That's why this little r should probably be a capital R. And then for the capital L, we basically use the fact that we're interested in the number of eigenvalues less than some number in a cutoff Coulomb potential. We'll just say, well, for those L, we'll take the full Coulomb potential. We can calculate that exactly. And when we do that, everything works out, and you get exactly the bound we need. That's it.
Any questions?
That should go back to the person.
Paul?
Give us an idea what is meant by subharmonic comparison theorems?
So you use the fact that two functions, well, one function was harmonic and one was subharmonic, and so the difference is harmonic, and use a maximum principle. It's not a deep fact. You can really just have to look what happens near the Coulomb singularity, what happens at infinity, and you get the part of the paper, this 70-page paper that we wrote, or 50-page, I don't remember now, that deals with what I'm talking about here is probably 10 pages at most. It's the paper, we decided to do the Thomas Fermi theory of solids and all sorts of other things that were interesting results. But what I said here is actually, it's not, none of it's very hard except maybe this Coulomb, pulling the Coulomb tooth, and it's all in the paper. It's actually a pretty readable paper, he said.
Any other questions?
I would like to know, in Thales' theorem, it's possible strong inequality? You know
we certainly expect it to be strong. We didn't, Teller didn't prove it, we didn't prove it, because the way the method of the proof happens to be of that form. But I suspect one could, in fact, prove it by essentially looking at the B. You basically take your centers and you move them away, and you can probably prove that so it's not stated that way in the literature, but I'll bet you could, at least in the literature at the time we wrote our paper, it's now 40 years later, somebody may have actually proven it. It should be true, but it's certainly not stated in our paper that, well, maybe it even is. Actually, I don't remember. It's 40 years ago. I don't want to think how many papers I've written since then. But I think we didn't have strict inequality. But I don't remember that for sure. It certainly should be true.